Hello, and welcome back to this tutorial series in OpenGL. So last time we talked about shaders and a bit about vertex data, or rather, pretty much how the VBO data gets from OpenGL memory onto your screen. And in this video, we're going to be creating a 2D camera that can pan around and zoom in and out. So to start off, we're going to be quickly revisiting the coordinate system that I talked about last episode. So in OpenGL, we use something called normalized device coordinates, of course. And if you remember, in this coordinate system, the left border of the window is -1 on the x-axis, and the right side is +1. And then for the y-axis, the top is +1 and the bottom is -1. And of course, 0, 0 is in the middle of the window. What we are going to be doing with our camera is that we are going to transform this coordinate system to instead be something like the following. So we want our left side of the window to be equal to 0, and the right side to be whatever width the window is. And in my case, it would be 800 since my window is 800 by 600. We're also transforming the y-axis to instead have 0 to be the top of the window, and whatever the height of the window to be the bottom, in this case 600. And then our origin will be at the top left. And if you've used other game development frameworks, you'll be very familiar with this kind of coordinate system. To actually do this coordinate transformation, we're going to be using a lot of linear algebra, actually. I won't be going into the exact math behind all of this, but I will of course link a few good resources on the actual math, and since there are plenty of information on the subject. What we're going to be doing though is creating what is called the projection matrix. This matrix is constructed in a way that shifts and maps the old coordinates to the new ones. We won't have to generate the matrix on our own. We'll instead make use of the namespace system.numerics, and it contains a bunch of useful classes like vectors, matrices, and a bunch of methods that are tied to linear algebra. So let's start making our camera. So start by making a new folder in the rendering folder, like that. We'll name it cameras, and in here create a new class, call it camera 2D. And like I said, the camera should be able to pan around and zoom in and out. So first of all, we need some kind of position for the camera. We'll use the class vector2 for this, as it contains an x and y coordinate in two-dimensional space. Name it focus position, since this position should be in the middle of the camera's view at all times. And then we just need a float for our zoom. Then create a quick constructor where we can input a starting position and a starting zoom for our camera. And then we really only need one other method for now, and that is the getProjectionMatrix method. It's going to return a matrix 4x4, which comes from the system.numerics namespace, and that is in fact the only type of matrix that we're going to be using throughout this entire tutorial series. In this method, we want to define which coordinates we want our camera to see by specifying which coordinates the left, right, bottom, and top border of the camera has. Since we want the camera's position to always be in the middle of the camera, we'll specify the left side of the camera to be the focus position's x position minus half the width of the window. And for the right side, we'll simply take the same x position and add half the width of the window. The top is the focus position's y minus half the height of the window, and the bottom is, of course, the y position plus half the height. Then we simply make a new matrix 4x4 and call it ortho matrix. And this is going to be where we create our projection matrix for the camera. It's going to be equal to matrix 4x4 dot create orthographic off center, and we just input the left, right, bottom, top variables. And then we say 0.01f and 100f. The last two numbers are the near plane and far plane, and it's basically how close and how far away stuff can be from the camera, but we are in 2D, so that doesn't make a lot of sense for us. So we'll just set it to some arbitrary values. Then we want our camera to be able to zoom in and out, so we need another matrix 4x4, and we'll call that zoom matrix, and it's going to be equal to matrix 4x4 dot create scale of zoom. Then all we have to do is return this orthographic matrix times the zoom matrix, and that is our entire camera 2D class. Now that we've made our camera class, we somehow have to use this actual camera, and that is usually done via the shaders. So for that, we have to use something called shader uniforms, and uniforms are basically variables inside of shaders that we can assign a value from our code. So let's head to our vertex shader code right here, and there we'll add a uniform mat4, which is a 4x4 matrix, and let's call it projection. Then we just have to multiply this vec4 down here with our new projection matrix, and make sure to multiply the matrix by the vector. This is important since matrix multiplication is not associative, just like normal multiplication. Now all that's left is to actually give this matrix an actual value in our code somewhere. So up top we can define a new camera object right here, camera 2D cam, and let's instantiate it down here. For the focus position, we'll just say that it should focus on half the width and height of the window, so window size divided by 2. And let's just set the zoom to 1. Now we're faced with the problem of actually giving our shader uniform the value of the projection matrix from the camera object. So to actually do this, we're going to have to go into our shader class and add some methods. So go into your shader class, and right down here we're going to need a new method, and we're going to call it public void set matrix 4x4. We need a string uniform name and a matrix 4x4. We'll call it mat. And this is the method that we're going to be calling when we want to set the projection matrix in the shader. So here we first of all have to call gl get uniform location of our program and uniform name, and save that in an int called location. This call will basically find at which location this specific uniform is placed in OpenGL memory, and then give back that location. After that, we call gl uniform matrix 4fv, just like that. Of location, we're going to be setting 1 matrix, and we do not want it to be transposed when we set it. And here it expects actually an array of float values. So it doesn't expect a matrix 4x4 object, which means that we somehow have to extract the values from the matrix 4x4 and put them in a float array in some specific order for OpenGL. Now, lucky for you guys, I have just the method for that. It's down in the description, and it looks just like this. All it does is it takes the values inside of the matrix and puts them in a specific order inside of a new float array. So right where the gl uniform matrix fv call expects a float array, we say get matrix 4x4 values of our matrix mat. And that's it. That is how we set a shader uniform. Now let's go back to our test game class, and right after the shader.use row, down in the render method, we write shader.setMatrix 4x4. The name is, of course, projection, and this should be our cam.getProjectionMatrix. Easy peasy. It's really important that we set this shader uniform after we've called use, since we're only able to set shader uniforms if we already have called use of an actual shader. If we try to start up now, you'll see that there won't be anything being rendered. But that is where you're wrong. Our shape is actually being rendered. However, instead of our VBO position data being interpreted as normalized device coordinates now, they're being interpreted as coordinates for our new coordinate systems. And all of our VBO positions are very close to 0, 0.5, 0.5, 0.5, 0.5. So these are the actual positions where our rectangle now is. They are all very close to the position 0. So if we instead make the camera focus on the position 0, 0, which is vector 2.0, and then we start it up again, we should see a very small dot in the middle of the screen. And that is in fact our rectangle, but it is a really small rectangle. In fact, it's only 1 pixel really. But we can of course fix this by using another matrix in our shader, usually called the model matrix. So let's quickly just close this down and set the camera to actually focus on half the window size. Perfect. So what about the model matrix? Well, it usually describes the shape's position, rotation, scale, and whatnot. Anything that describes where and how the shape is in the world. So let's add a new matrix to our vertex shader and call it model, and stick it in right there. Make sure to not mix up the order here. Like I said, multiplicative associativity is not a luxury we have with matrices. Then all we have to do is set this model to a matrix 4x4 somewhere in the code. But which matrix 4x4? It was pretty clear for the projection matrix that it should be the camera's projection matrix, but what about this one? Well, it all depends really on what we want to do, but it's basically like this. So let's go down to the render method. Here we start by just defining where and how we want our shape to be in the world. I want it to be at a position 400, 300, which I can do with a vector 2. And then I want it to be scaled to be 150 pixels wide and 100 pixels tall, which I also can do with a vector 2. And lastly, I want it to be rotated at an angle of 45 degrees. Then all we have to do is create a couple of matrices that describe this. So we start with the translation matrix, which is the shape's position. We create a new matrix 4x4, call it trans, and it is going to be equal to matrix 4x4.create translation of position x and position y, and let's just say 0 at the z position. And then we move on to the scaling matrix, which is pretty much just the same. We call matrix 4x4.create scale of scale x and scale y, and then 1 in the z scale. Then we need a matrix for the rotation, which is also a piece of cake. We just call matrix 4x4.create rotation z of rotation. A quick note on why we actually use the Z rotation is that our coordinate system only really has two dimensions, x and y, but the third dimension actually exists as well. It's just that we aren't using it. And since the x and y coordinates define our 2D space, the third z-axis would define the depth, which would then be pointed straight from your nose towards your screen. And if we want to rotate our 2D things, we want them to rotate around this axis that goes from your nose to the screen to actually rotate in a manner that makes sense in our 2D case. You could of course try rotating them with x and y as well, but wouldn't make much sense. Anyway, with these three matrices, we have all we need to define our shape's world position, size, and rotation. We simply call shader.setMatrix 4x4, and it is the model matrix, and we say scaling times rot times trans. Also, note the order of these as we still don't have associativity for matrix multiplication. Now, if we start it, we see that the shape is positioned at 400, 300, which is middle of the screen. It is slightly wider than it is high, and it is at a 45-degree angle. To make it a little more interesting, why not set the rotation of it to be, for example, mathf.sine of gametime.total elapsed seconds times mathf.pi times 2f. And let's actually zoom the camera in a bit to 2.5, like that. And let's start it up. And there we go. Very pretty. So in this video, we covered a bit on different coordinate systems. We created our own 2D camera, which we can move around and zoom in and out. We also talked a little bit about how we can describe a shape's position, size, and rotation in our world by using different matrices. And of course, in the upcoming videos, we'll talk about textures, how to load them, how to store them in OpenGL memory, and of course, how to render them. That is all for this video. Make sure to like and subscribe if you want to see more of these videos. And it's been great to see that so many of you guys appreciate these videos. I'll see you in the next one. Thanks for watching.